I appreciate Dr. Borse also. And I once again welcome all the participants. And in 2 days workshop, we will get the benefit definitely. And I wish you all the best, Dr. Borse, sir.
Thank you, sir. So now I am sharing my screen. Is it visible? Screen is visible? Is the screen visible?
Yes, sir. It is visible.
Yeah. Now, purpose of today's session is not micro channel, but conventional channel. Then, so that you can have some questions, how it is different from conventional fluid flow and heat transfer. Okay, that is the purpose of today's lecture. Okay, so we'll just revise fluid flow and heat transfer in conventional channel, so that we can ask some questions tomorrow in the session related to the macro channel. Okay, so I will just go to the presentation mode. Okay, is my PPT visible? Hello?
Yes, sir, it is visible.
Yeah. So we'll just revise fluid flow and heat transfer in conventional channel means channel having dimensional more than 1 mm. So is it visible now?
Yes.
Direction of heat flow, PPT. Yeah. Okay, we are aware that heat flows from higher temperature to the lower temperature, like the water flows from high level to the low level. Okay. So hot object in the cooler room will cool to the room temperature. Suppose we keep any hot object in the room, then it will become cool after the few minutes. Okay. Okay. If you put cold object in warmer room, it will heat up to the room temperature. Okay. So what happens in the heat transfer? Body try to reach to equilibrium with the surrounding. Okay. So now we'll see the modes of heat transfer. Basically, the modes of heat transfer is a mechanism by which heat transfer takes place, is called as what? Modes of heat transfer. So what I'm doing, I'm taking the revision of both heat transfer and fluid mechanics. Okay. So there are three modes of heat transfer: conduction, convection, and radiation. Now, before going to this, we'll just see what are the applications of heat transfer. So wherever there is temperature difference between surrounding and the object, we call that is the application of heat transfer, like gas turbines, then heat exchanger. You can see here heat exchanger, then turbine blade, then comes engine cooling, electronic cooling, cooling in the cooking, like home appliances like geyser, iron, air heater, okay, refrigerator, air conditioning, solar energy application. These all fall in the category of application of heat transfer. Now let us understand what is different modes like conduction, which occurs in all the modes, solid, liquid, and gas. So when it occurs in the gas, there is no gas moment. Okay. So what is the governing law? It is Fourier's law. In convection, it happens in liquid and gas. Governing equation is Newton's law of cooling. Radiation occurs, you don't need any medium. Okay, so if there is no medium, there is better radiation. If there is medium like air, like we receive the radiation from the sun, It is because of radiation. Okay, there is no medium, still it can travel. Okay, for convection, if there is no medium, no heat transfer. Conduction, no medium, no heat transfer. But in radiation, without medium, it can radiate. So governing law is Stephen-Boltzmann law. Now comes governing equation in conduction. In conduction, the heat transfer is directly proportional to the temperature gradient and area. Okay, where constant of proportionality comes to be K. K is what? Material property. Please understand. In convection, K is proportional to temperature difference between the surface and surrounding fluid and area. So constant of proportionality come here H. H is called as what? Convective heat transfer coefficient. Okay, it is not the constant like material property in the conduction. In the radiation, heat transfer is directly proportional to the fourth power of absolute temperature and area. Okay. And constant of proportionality is absolute constant, sigma, that is called as Stephen-Boltzmann constant, is the absolute constant. It is a 5.67 into 10 raised to 8. Is it audible? It is visible? Hello?
Yes, sir. It is
Yeah,
visible and also audible.
Yeah. Now we'll see the mechanism in conduction occurs because of migration of free electrons. Okay, that is called as drift of free electrons. Conduction occurs because there is one more that is a lattice vibration, and convection that we are interested more here is because of fluid motion. As long as there is a fluid motion, there is a convection. Whether this motion is created naturally, then it is called as natural convection. If it is created forcefully, it is called as what? Forced convection. In the radiation, it is because of propagation of electromagnetic wave. Okay. It is because of electromagnetic wave. Okay. So I think there is some. Okay, so we'll see what is the engineering problem. So engineering problem is in heat transfer. The task of engineer is to design and size the thermal equipment. Here, the purpose is to either estimate temperature distribution or to estimate heat transfer. Is it audible?
Yes, sir.
Yeah, audible and visible. Yeah. Okay.
Yes, sir.
Yeah. Now, as a thermal engineer, what is our purpose is that we have to achieve desired heat transfer. And when this transfer occurs, we have to also see about the pressure drop of the our fluid in the forced convection. Okay, it should be reasonable. It should not high, because then operating cost of heat transfer equipment will be very high. Okay. Now we'll go to the natural convection. As I mentioned, natural convection Here the fluid motion is created naturally because of buoyancy effects. Like the lighter fluid will move up and heavier fluid will come down. Generally, what happens as the temperature increases, the fluid becomes lighter, and as the temperature reduces, it becomes heavier. So heavier will move down and lighter will move up. Because of that, there are the flow of the fluid is created. Okay. But what is the drawback of natural convection? We cannot achieve the high rate of heat transfer in natural convection. It is desired that you should start your design with natural convection. It is desired that you should start your design with natural convection and see whether you are getting desired heat transfer or not. Okay. If you are not getting desired heat transfer, then you have to move to the next heat transfer, that is called as forced convection. Here the flow is created artificial with the help of some fan, blower, compressor, or pump. Okay. So these devices needs energy for operational. So we have to take the decision for forced convection only if it is required. Okay. Only if it is required. Okay. Only if it is required. Okay. So if it is not required, then don't go for forced convection. Okay. Now, the forced convection, we need extra energy, money for creating the motion of fluid. Okay, so only go for forced convection if it is needed. Now we'll just see the difference. As I mentioned, we start your design. We start your design with the forced convection. If it is not possible, then you go for forced convection. Okay. So what is the drawback of natural convection? Heat transfer is less, and in forced convection, heat transfer is more. But it is a free. Natural convection is free. Okay, we don't need any external power for moving the fluid, but in the forced convection, we need the external power. Why the heat transfer is less? Because convective heat transfer coefficient is less in the natural convection. Why here heat transfer is more in forced convection? Because heat transfer coefficient is higher. So let us see now which dimensionless parameter are related here. Grashof number, nussel number, and Prandtl number in the natural convection. In the forced convection, instead of Grashof number, Reynolds number, then there is nussel number, same number, Prandtl number. Okay. In the forced convection, there is a Reynolds number, and in natural convection, there is a Grashof number. Okay, now we'll see one by one Grashof number. So Grashof number is buoyancy force into inertial force divided by viscous force square. Okay, Grashof number is used in a natural convection, as I mentioned earlier. Okay, where nu is kinematic viscosity, that is dynamic viscosity divided by density. And beta is 1 by TF, that is beta is coefficient of volumetric expansion. TF is a film temperature. Okay. Then we'll go for a Reynolds number. Reynolds number is what? Inertial force divided by viscous force. So it tells which force is dominating. Which force is dominating. Okay. Which force is dominating. It tells about what? Which force is dominating. Okay. Which force is dominating. It tells about which force is dominating. I think there is some chart. So I'll just go to participant. We'll just go to the PPT again. Please understand. So today's discussion, tomorrow's discussion, Reynolds number is very much important. Okay, it is the ratio of inertial force to the viscous force. Okay, what is the inertial force? Inertial force is because of velocity, and viscous force is because of viscosity. We know that laminar flow is a viscous effect, so it happens at lower Reynolds number, and turbulent occurs at a higher Reynolds number. So Reynolds number is the one we use to describe whether the flow is laminar or turbulent in the channel, as well as for external flow. So if you see the formula rho v d by mu, it indicates that you go for, it indicates that if you go for smaller diameter, the flow will go towards the laminar range. Okay, so what I mentioned, now we are today I am discussing the channel with the diameter more than 1 mm, but tomorrow we'll discuss about what? Channel with the diameter less than 1 mm. Okay, so as we go to the smaller and smaller diameter, basically we move towards the laminar flow. Okay, so it describes Reynolds number whether the flow is laminar or turbulent. Okay, so I have mentioned in the next slide that if your Reynolds number is below 4000, it is a laminar. If your Reynolds number is above that, it is a turbulent. Okay, so this number slightly changes. There is what is called as transition in between. Okay, so I already mentioned here, if your Reynolds number is less than 2300, it becomes laminar. If your Reynolds number is more than 4000, it becomes turbulent. In between, it is a transition. Please understand, there are advantages of laminar flow. There are drawbacks of laminar flow. What is the advantage of laminar flow? Can anyone tell me what is the advantage of laminar flow? Advantage of laminar flow. What is the advantage of laminar flow? Can anyone tell? So advantage of laminar flow is that there is a less pressure drop. We require less energy to pump. Okay. But their drawback is what? There is a less heat transfer. Please understand. Pressure drop is less as well as heat transfer is less. Pressure drop is less as well as what? Heat transfer is less. In turbulent flow, what happens? Pressure drop is more and heat transfer is more. Now this is about flow through the duct. Now flow over the surface, we have to decide based on the Reynolds number. If it is more than 3 × 10⁵, it is a laminar flow. If it is less than this, if it is more than 5 × 10⁵, it is a turbulent flow. For the external flow, like flow over the surface. Now this was for what? Flow through the pipe or duct. Okay. So basically, Reynolds number tells us whether the flow is laminar or turbulent. Clear? And we also understood here in the Reynolds number that if you go on reducing the diameter, the flow becomes laminar. If you go on reducing the diameter, what happens? Flow becomes what? Laminar. Okay. Flow becomes laminar. Flow becomes laminar. So we'll just move to PPT again. Now comes a dimensionless number. Now we are actually discussing what? Dimensionless number, like we saw Reynolds number, Regressive number. So why we go for dimensionless number? Because if you use variables, then we require large number of experimentation. Okay. So to reduce the number of variables, what we do? We combine with dimensional analysis, this variable, and we get dimensionless parameters. This number of dimensionless parameters are less than number of variables. So what happens? Our experimentation get reduced. Okay, that is the purpose of using the dimensionless parameter. Also, describing a phenomenon in dimensionless parameter, it's also reduces number of equation. So nussel number, like Reynolds number is used for what? Generally, it is for fluid flow. Okay, fluid flow. But nussel number, it is used related to what? It is a heat transfer. So what is the formula for nussel number? It is a HL by K, where K is thermal conductivity of fluid, H is a convective transfer, and L is a some parameter. Okay, it is a diameter in case of flow through the pipe. It is the length if you are dealing with the external flow. Okay, so if you see, this is the nussel number, which comes both in the natural convection as well as forced convection. Then comes one number called as Prandtl number. Similar to the nussel number, it is also appears in both forced as well as natural convection. Reynolds number only occurs in what? Forced convection. Regressive number occurs in natural convection. But nussel number and Prandtl number occur in both forced and natural convection. So Prandtl number tells that which diffusion is faster. It tells that which diffusion is faster, whether momentum diffusion or thermal diffusion. Okay. Okay, which diffusion is dominating? Which diffusion is dominating? It is mentioned by which diffusion is dominating? It is mentioned by what? Prandtl number. Okay. Which diffusion is dominating, whether it is the flow diffusion or thermal diffusion. Okay. So we know that Prandtl number for air is about 0.7. What's the meaning of that? Which is dominating, thermal diffusion or momentum diffusion? For air, Prandtl number is 0.7. So which is bigger? Thermal diffusion is bigger than the momentum diffusion. Okay. Which velocity diffuse faster or temperature? So temperature diffuse faster for air, but it is mostly nearly to the 1. Then for natural convection, there is one more number called as Rayleigh number, described by the RA. Okay. So it is a Prandtl number into the Regressive number. Okay. That multiplication is called as Rayleigh number. So what is the use of Rayleigh number? Like in forced convection, we saw Reynolds number tells us whether the flow is laminar or turbulent. Reynolds number tells what in forced convection? The whether flow is laminar or turbulent. Similar. Okay. Similarly, Rayleigh number tells us whether the flow is laminar or turbulent for natural convection. Please understand, there can be the flow turbulent in the natural convection. What is the criteria? Rayleigh number. If Rayleigh number is less than 10⁹, it is a laminar flow. If it is greater than 10⁹, it is the turbulent flow. It is the turbulent flow. Okay, it is the turbulence. So what is the use of Rayleigh number? Use of Rayleigh number is to tell in the natural convection, whether it is a laminar or turbulent. Okay. Whether it is a laminar or turbulent. Whether the flow is laminar or turbulent. Okay. That is the use of Rayleigh number. Then one more number comes Stanton number, which is the ratio of nussel number divided by Reynolds number, Prandtl number. Okay. Then comes Peclet number. Peclet number is advective transport. It is an advective transport. So it is what? Advective transport divided by diffusive transport. Okay. So it is simply the multiplication of Reynolds number and Peclet number. It is used in the force convection. So comes how to like I told you, HL by K for nussel number. So that hydraulic diameter, it is how it is calculated 4A by P, where A is cross-sectional area, P is the cross-sectional perimeter. Okay. What is A is cross-sectional area, P is the cross-sectional perimeter. Like here I have seen shown some cross-sectional, like if it is circular, then hydraulic diameter is what? Diameter of pipe. If it is square, then it is side of the square. If it is a rectangle, then it is the what? It will be 2BC by B plus C. Same formula we have to use 4A by P. Okay. Same formula we have to use 4A by P. Okay. Now here I have shown one example how to calculate hydraulic diameter. So Ri is the inner diameter, Ro is the outer diameter. So 4A by P we have to take. Okay. So 4 pi Ro square minus Ra square divided by perimeter. It will be which perimeter? 2 pi Ro plus 2 pi Ri. So if you simplify, it becomes 2 times Ro minus Ri. If your flow is inside the annular passage. If your flow is inside the annular passage. Okay. Now, please understand, when we write Navier-Stokes equation, so Navier-Stokes equation is what? Actually, it is a momentum equation. Navier-Stokes equation is what? Actually, momentum equation. We know that Newton's first law tells definition of force, and Newton's second law gives the equation of force. So that is the Newton's second law. What it tells? Newton's second law tells us that it tells that force is equals to mass into acceleration, or summation of force is equals to what? Mass into acceleration. That equation is nothing but what? Navier-Stokes equation. Okay. Newton's second law we write for the fluid, and that comes out to be what? Navier-Stokes equation. But in Navier-Stokes equation, what we take? Viscosity. And in Euler equation, we neglect the viscous force. That is the viscosity. We neglect the viscosity in which flow? Euler flow. Okay. So I will just go in the next slide that I will tell you. I think I can fast. Okay. So as I mentioned, if I write this Newton's second law, then if I write a Newton's second law for viscous flow, then it becomes what? Navier-Stokes equation. So what is that? Mass into acceleration is equals to what? Summation of forces. Which forces occurs in macro flow? Pressure force, viscous force, body force, that is a gravity. And if it is a turbulent, then there will be turbulent force. Okay. So that equation is called as what? Navier-Stokes equation. Okay, but if you neglect viscous force, if you neglect viscous force, then it will become what? It will become what? Euler equation. Please understand. Euler equation. When friction is very negligible, then we go for Euler equation. Otherwise, we go for what? Navier-Stokes equation. We go for what? Navier-Stokes equation. It is the Navier-Stokes equation. You know that Navier-Stokes equation, there are three equations. Why there are three equations? Because it is about the force. Please understand. Navier-Stokes equation. Why there are three equations? Because it is a force, and force is a vector quantity. Force is a vector quantity. So there is a force in x direction, force in y direction, and force in z direction. So there will be three equations. Okay. So we generally don't use Euler equation because viscosity effect is always there. This viscosity effect is less at high speed for aeronautical people. So earlier, when there were limited resources, when there was a limited resources, people were going with what? Euler equation. But people don't go now with the Euler equation, to go with the Navier-Stokes equation. And Navier-Stokes equation are three. One is in x direction, y direction, and z direction. What is that meaning of that? Summation of forces is equals to what? Mass into acceleration, where A acceleration is there in that particular direction, force in that particular direction. Okay. If you neglect viscosity, then it becomes Euler equation. Navier-Stokes becomes Euler equation if you neglect the viscosity. One more concept which is related to fluid mechanics is what? Bernoulli's equation. Okay. What is that equation? Bernoulli's equation. Okay. What it tells, there's summation of pressure head. Suppose this is a random pipe. This is a random pipe. This is the inlet. This is the outlet of pipe. So at this location, Z is the datum. Here velocity is V. Pressure is P1. Velocity is V1. Pressure is P1. At this location, our exit velocity is V2. Pressure is P2, and datum is Z2. So we take datum from some reference, common reference. Okay. So it tells that summation of pressure head, velocity head, and datum head. Summation of pressure head given by rho g, some plus velocity head v1 square by 2g plus z1 is equals to what? P2 by rho g plus v2 square by 2g plus z2. So in Bernoulli's equation, we assume that there is no friction loss. But in reality, what happens? There is a friction loss between the 2 points. So we have to account this pressure loss. We have to account this pressure loss. We have to account this pressure loss. How we account? By adding the head loss. By adding the head loss. Okay. To the downstream side. Which side we add the head loss? Downstream side means two sides. Okay. One is upstream and downstream. Okay. One is upstream and two is what? Downstream. Okay. So downstream side we have to add the head loss. Okay. Then it becomes the modified and Bernoulli's equation. It becomes modified and Bernoulli's equation, and we use it. Okay. So what it gives? Bernoulli's equation gives the relation between a pressure, velocity, and datum head. What it gives? Bernoulli's equation, it gives relation between the pressure, velocity, and datum. Okay. This becomes very useful for solving the problem. Now, it may occur that, so what basically we do, we use some correlation for calculation. So if it is a natural convection, we use the correlation of natural convection. If it is forced convection, then we use the relation of forced convection. But what happens? There may be mix of both. Okay. So how to decide which equation to be considered? So we decide based on the ratio of GR, that is the Grashof number divided by Reynolds square. If Grashof divided by Reynolds square is very, very small than 1, then we say that what is dominating is denominator, that is the Reynolds number. So Reynolds number is related to force convection. So force convection is dominating and natural convection is negligible. If GR by Reynolds square is greater than, very, very greater than 1, it means what? What is dominating? Natural convection, and we can neglect the force convection. But if GR by Reynolds square is near to 1, then we can say both are important. Then it is called as what? Mixed convection. Then we have to use the relation of what? Mixed convection. We have to use the relation of mixed convection. Now we are now in the force convection. Force convection is of two types. It is external flow, like over the surface, or the plate, or the aeroplane. It is what? External convection. And internal convection means what? Flow through the tube, pipe, duct. Okay. Now see the external convection or external flow. Then we'll see that there is a boundary layer is formed. Boundary layer means what? It is a gradient. Like, I'll just switch on the marker. Like the here the piston velocity is u infinity, but the fluid touches the boundary, the velocity becomes 0. Near to wall, what is called as no slip condition. Okay, so velocity of fluid becomes 0, but surrounding is u infinity. So the velocity varies from 0 to the surrounding velocity. So such layer is formed. That layer is called as boundary layer. Okay, that layer is called as what? Boundary layer. Okay, so for initial reason it is a laminar, then become transition, and then it becomes turbulent. Okay, it becomes turbulent later on. Okay, so such boundary layer is formed. Okay. So if you solve the equation for this boundary layer, okay, then we can get different parameter like equation for nussel number. We can get boundary layer thickness. Then we can get skin friction coefficient. Okay. Then we can get average nussel number. Our interest is what? In the heat transfer, average nussel number. Okay. So for external flow, there is a called as Reynolds analogy, which relate the skin friction coefficient, okay, with the Stanton number, that is Cfx by 2 is equals to Stanton number, okay, and which is valid for Prandtl number 1, Reynolds analogy, and Colburn analogy. Prandtl number changes from point where it is applicable if Prandtl number 0.5 to 50. So Stanton number into Prandtl raised to 2 by 3 is equals to Cfx by 2. Okay, this is just similarity between the friction loss and the heat transfer. Okay, for the boundary layer. For the boundary layer. Okay. Similarly, there are the relations for the turbulent boundary layer. These are the relation for laminar, and this is for turbulent boundary layer. Okay. And these are the relation for mixed boundary layer. Okay. Now, this is our main topic. Mechanical engineer mostly deals with the flow in the pipe, tubes, and duct. So, flow in the tube is either laminar or turbulent or mixed flow. Please understand, not like external flow where it is a mix of laminar, turbulent, and transition, but in the flow in the duct, what happens? It is either laminar or turbulent based on the Reynolds number. Like I told, if it is less than 2300 Reynolds number, flow is laminar, and if it is more than 4000, it is turbulent. Okay, it is turbulent if Reynolds number is more than 4000. Now, please understand, when we talk about laminar flow, friction factor is given by a simple relation. Friction factor is given by 64 by Re for laminar flow. How it is given? 64 by Re for laminar flow. What? Friction factor. But for turbulent flow, it is not a single relation. It is not a single relation, friction factor. But what we have to do is, we have to use one chart called as Moody chart. Which chart we have to use for turbulent flow? Moody chart. I will just show you Moody chart. If you see the Moody chart, what is the Moody chart gives? It gives the friction factor. Now, if you see the laminar range, there is single line. Laminar flow, there is a single line. Laminar flow, there is single line, that is a 64 by Re. But if you see the turbulent flow, there are different lines. There are different lines for the turbulent flow. Okay. Based on what? Relative roughness. Based on what? Relative roughness. Why there are different lines? Why there are different lines in turbulent flow? Because the friction factor depends on what? Relative roughness of the surface of the pipe. It depends on what? Relative roughness of surface of pipe. But in the laminar flow, it doesn't depend on the roughness of pipe. Please understand. What happens in the laminar? Friction factor does not depend on the roughness of the pipe. Basically, what happens when we go to the smaller diameters, we go toward the what? Laminar range. Because if you see the equation of Reynolds number, it is a rho v d by mu, means it depends on diameter. If you reduce the diameter, Reynolds number reduces. Okay. In turbulent flow, what happens? The friction factor depends on the wall roughness, relative roughness. Okay. But in the laminar flow, it does not depend on the wall roughness. So there is single formula for friction factor, that is a 64 by Re. But you see for turbulent flow, based on the relative roughness, there will be different line for friction factor. Okay, so many times for simplicity, we consider very smooth pipe. Okay, but that is the approximation. Okay. So from the heat transfer point of view, we get more heat transfer in turbulent flow, less heat transfer in the what is called as the laminar flow. Now we'll also understand when we go for the pipes. So we have to understand losses. Pressure loss occurs because of friction, that is called as major loss. And there are also other losses like bends, fittings, walls, then exits. All this causes losses that are called as minor losses. Okay. Why major loss is called as major loss? Because in mechanical piping, the length of pipe is very, very large as compared to the losses, bends. Okay. So we call it as a major loss. Okay. Minor losses are because of what? Because of bends, tees, exits, inlet, walls. Okay. Solving with the major load friction law, FLV square by 2GT. So where F is the friction factor that we have to take from the Moody chart based on the Reynolds number. L is the length of pipe. P is the velocity. D is the diameter. Okay. So this is the Moody chart you need to use for finding the friction factor. So what we are talking here for the macro channels, channels more than 1 mm. So tomorrow we'll ask Dr. Agrawal sir to give more light which equation we have to use for macro channel. Okay, these are the losses. Exit loss we calculate like this. It is V1 square minus VT square divided by 2G. This is the contraction loss if there is sudden reduction in the pipe diameter. This is loss because of bend. Okay, so this loss coefficient K elbow are available in the books or the manuals. Okay, design manuals, it will be available. Okay. Now, as I mentioned, that wall roughness, as I mentioned, wall roughness in the laminar flow will not affect your friction factor. Wall roughness in the laminar flow will not affect your heat transfer. Okay, so friction factor is only one relation, whether it is smooth or rough for the laminar flow. It is a 64 by RE. Okay, same thing for the heat transfer. In the heat transfer, based on the condition, whether it is a constant wall temperature or constant heat flux, there will be a constant value of nussel number that we'll see. Okay, now we can see here when flow enters in the tube. When a flow enters in the tube, what happens to its velocity profile? What happens to its velocity profile? Okay, you can see here. Here at the inlet, I will just switch on the marker. Here the velocity is uniform, but as it enters near the wall, we know that what is the velocity near the wall? 0. So the velocity changes here from 0 to the velocity with which the fluid is coming. So it slowly forms the velocity profile because still the flow is fully developed. Please understand, it is a developing length. Okay, this length till it develops, it is called as what? Developing length. Okay, for laminar flow, this profile is parabolic. For turbulent flow, it is hyperbolic. Okay, what happens till the flow develops? The friction factor will not be will be different. Like we say, it is 64 by RE, but it is for only developed flow. But for developing flow, we have to use some other relation. Okay, please understand. Now here I want to tell you that in the turbulent flow, the profile is different. It is more flat near the center, but in turbulent laminar flow, it is like this, parabolic. Here it is logarithmic or hyperbolic. Okay. Please understand, roughness is very important in turbulent flow. Okay. whether it is heat transfer or friction factor. But roughness is not important in the laminar flow. Please understand. Okay. Doesn't create much difference in case of laminar flow. Now we'll see the two type of boundary condition here. One for the laminar flow or heat transfer. Okay, laminar flow heat transfer. This is the heat flux is constant. Here, what happens? The bulk temperature, fluid temperature goes on increasing. Suppose fluid is moving. This fluid is moving like this. So as the fluid moves, its temperature goes on increasing because wall temperature is bigger than that. Okay, wall temperature here, there is heat is given. Heat is given to the fluid, so temperature goes on increasing for the fluid as it comes out. As it comes out, temperature goes on in the same way. What happens to the wall of this tube? Temperature goes on increasing. Okay, temperature goes on increasing. After, once the profile is developed, this temperature difference don't change. It becomes parallel. Okay, it becomes parallel. Temperature difference become constant. Temperature difference become constant. Okay. Now we will see for constant wall temperature. The temperature is constant and it is bigger than the fluid temperature. So fluid temperature will go on increasing. Okay. So this difference will go on reducing. This difference will go on reducing. Okay. This temperature difference will be go on reducing. So there will be single value for nussel number. Okay. There will be single value for the nussel number. Okay. There will be single value for the nussel number. Okay. So that value I am telling here. Okay. It is 3.66 and 4.36. Okay. Now what happens? These values are constant. If it is a laminar flow is there and it is developed, then in one case it is 4.36, in another case it is a 3.66. But what happens if the flow is developing in the entry region? Flow is developing, then we cannot use this constant values. Okay, 4.36 is for what? Heat flux. If the Q is constant, then nussel number is how much? Nussel number is 4.66. If it is the Q is constant. Please understand, nussel number in case of laminar flow. Nussel number in case of laminar flow depends on what? Boundary condition. If it is constant heat flux, then it is 4.36. If it is a constant temperature, nussel number value is constant and it is a 3.66. It is a 3.66. Okay. But it is only for developed region when flow is developed. When thermal boundary layer is developed. If it is not developed, then it is varies like this. Okay. So we have to use some relations. So we use the Grace number and then we calculate. We use some relation for entry region. Entry region, we use some correlations. Okay. Now question comes of entry length. Entry length means what? Till the flow develops, that is called as entry length. Till the flow develops, it is called as entry length. And we cannot use this relation that nussel number is 4.66 for constant heat flux, or it is 3.66 for constant temperature. Okay. So we have to calculate entry length. So how we calculate entry length? How we calculate entry length? We use the for thermal boundary layer. Entry length is calculated as 0.05 d into Reynolds number into Prandtl number. Okay. This one's length, we cannot use the relation. In this region, we have to use the different relation, developing relations. Okay. But in developed flow, for constant heat flux, in laminar flow, nussel number is 3.66. For constant wall temperature, it is a 3.66. For constant wall heat flux, it is a 4.36. And friction factor is also 64 by RE. So if you deal with the laminar flow, it is very easy to calculate. Okay. If you deal with the laminar flow, it is very, very easy to calculate. Okay. Now, when we calculate the properties, we have to use what? Bulk temperature. We have to take the average temperature of inlet and outlet. Okay. We take the average of inlet and outlet. Now, when we deal with laminar flow, it is very, very easy for heat transfer and fluid flow. But as soon as we go to the turbulent region, even for friction factor, it depends on the wall roughness. So it is not one relation, there are many relations. Okay. If you go with the heat transfer also, there is a relation and it is not constant value. Here it depends on what? Reynolds number and Prandtl number. It also depends on whether it is cooling or heating. So generally we use for smooth duct, Dieter-Bolter relation. We use the Dieter-Bolter relation. Okay. For the smooth duct, for heating and cooling. Okay, this is the friction factor. You can calculate from Moody chart. Now, as I discuss how we arrive this dimensionless parameter, it is because of what? Dimensional analysis. If you do dimensional analysis, if you see which parameters are affecting force convection and using the Buckingham pi theorem, we can, if there are basic variables are 7 and basic dimension, that is mass, length, time, and temperature, there are 4. So we can get how many dimensionless parameters? 7 minus 4, that is the 3. So we get the 3 numbers like Reynolds number, nussel number, Prandtl number. Okay. So this is the Nusselt, Nusselt, Reynolds number, Reynolds, Osborne Reynolds, you can see. So Reynolds number tell us whether the flow is laminar, turbulent, for force convection, and Rayleigh number, which tells us whether the flow is laminar or turbulent for the natural convection. So this is all about, we can say, a little revision about fluid flow and heat transfer. If you have any question and doubt, we can ask. But today's session is only on macro channel. Macro means what? More than 1 mm. Okay. Tomorrow we'll see details about microchannels by Professor Dr. Amit Agrawal from IIT Bombay. If you have any question, so why arrange this session so that you will be able to compare very easily what is a macro channel flow and micro channel flow. Okay. So we can ask tomorrow question whether how much it is similar to this. Okay. Yes, please. Yes. Is there any question? Hello. Is there any doubt or question?
No question, sir.
No
Okay.
questions, sir.
Okay. Thank you. Tomorrow, please join before the 10 a.m. so that you not miss the important points, and you can ask the doubt based on today's session. Okay. Thank you. Thank you for attending this session. Thank you.
Thank you, sir.
Thank you, sir.